Thank you so much, and it's such a pleasure to be here again at the IPGP to speak about things that I find so fascinating and moving. We live on a planet of breathtaking beauty, and when you see Earth from the proximity of our moon, you see those swirling white clouds, the blue ocean, and it's natural to ask, has Earth always looked like this? And if it's changed, how has it changed? And indeed, is Earth unique amongst the worlds in our cosmos? And I would like to look today at a way of perhaps answering some of these questions, gaining insight. And it's a new approach that we're calling mineral ecology. Mineral ecology is the examination of the distribution, the disparity, and the diversity of minerals in Earth's surface, and looking at this through Earth history. This approach leads to some new questions. It leads to questions about the changing physical, chemical, and biological environments in which minerals form. And it also raises questions about the uniqueness of our planet and the mineralogy of other worlds as well. So a question I want to address today is, if you replayed the tape of Earth, or had another Earth-like planet, would the mineralogy be the same? Or in some respects, would it be quite different? That's what we're exploring today. Now, to begin with, this all stemmed out of the study that we call mineral evolution, which is looking at the changes in Earth's near-surface mineralogy through time. And I have many, many colleagues that I have to credit. This has been an international and a very diverse group of people who have helped. And this is just a partial list of the people who have been involved. There are actually many more at this point. And I'm delighted to be able to work with so many interesting people. So mineral evolution involves several changes of Earth's near-surface mineralogy. Certainly the change in the diversity of minerals, because the range of minerals we see at Earth's surface has increased dramatically through the 4.5 billion years of Earth's history. It also has to do with the relative abundances of those minerals. Their compositions, particularly the trace and minor element compositions of minerals, also the isotopic compositions, these have changed through time. And something that, as a mineral collector when I was very young, was important to me: the colors, the sizes, the shapes of minerals, the things we see in the great museum collections, but which mineralogists have pretty much ignored. It turns out that those too show dramatic changes through Earth history, and they too tell a story. So these are all aspects of mineral evolution. Now, we focus exclusively on the near-surface environment for a number of reasons. That's the part of Earth that's most readily available to study. We could extend mineral evolution into the mantle, but that's not been done yet. It's something that's on our radar screen, and certainly both for the Geophysical Laboratory and IPGP, who think so much about high-temperature, high-pressure environments. This is a direction we'd like to pursue. It also this is the type of mineralogy we're going to see when we examine other planets and moons. So near surface becomes very important in studying Mars or Mercury or the moon, for example. And this is the part of mineralogy that interacts directly with biology. And it will turn out that biology plays an incredibly important role in Earth's evolving mineralogy. So, a comment on the word evolution. A number of people have objected strenuously to us talking about evolution in terms of minerals. They say, no, that only applies to biology. And I disagree, because evolution has a number of meanings that change over time, and you all know Norman Bowen's evolution of igneous rocks. We talk about the evolution of meteorites, and we can talk about the evolution of minerals. And what we mean are the number of things. First of all, this idea of diversification, of complexification over time. In other words, any system in which you start with simplicity and you see gradual increase in diversity can be said to evolve. In mineralogy, as in many other systems, we see congruency. That means each stage of mineral evolution follows logically from the stage that came before. And so this is not just some random set of happenings, it's a sequence. But it's not Darwinian evolution. It's certainly not natural selection in the sense that biology means so we don't have to think about this. I will say the thing that makes evolving systems similar to each other are the following. Every evolving system has to have some sort of combinatorial richness. There has to be agents or elements that can be juxtaposed in many, many different ways. you need to have then a way to sample that richness through mutations, through, on Earth, many different environments with different temperature, pressures, and compositions. And then you need to have a selection mechanism of some sort. And of course, in mineralogy, the selection mechanism has to do with thermodynamic stability and conditions, and then the kinetics of some minerals being preserved in their metastable state. But in every evolving system, these are true, and it's true for mineralogy as well. So the idea here is that new minerals arise from physical, chemical, and biological processes, and we're going to look at those processes for deep time. To give you a sense of what's different about mineral evolution than what came before, this question. I have scoured the literature. I have looked over the mineralogical literature for the last 200 years. I cannot find any mention of a question like this, which is shocking. This is not one of the most basic things to ask about a discipline, the origins. We talk about the origin of life, we talk about the origin of planets, we talk about the origin of the cosmos and the Big Bang. But mineralogists, it seems, have not asked the question, what was the first crystalline compound in the cosmos? And so some of you will know the answer, but I ask you to think about this. How do you get the first crystal? Well, you couldn't have had it at the Big Bang, because the Big Bang was much too hot, and even after a few 100,000 years of processing, all you had was hydrogen and helium, perhaps a little bit of lithium, and those simply won't form crystalline compounds. So then you have to make the first stars. And you make those first stars, and they go through the processes of nucleosynthesis, and you make carbon, and you make the heavier elements one by one. Some of those stars are very energetic. They have gaseous envelopes which are radiating outward and cooling. Others explode in supernova. And so think about that very early period of the cosmos for the first exploding stars. And here, for the first time, you have an environment in which you have mineral-forming elements, and it's cool enough to condense those elements. And so I would argue that the very first crystal in the cosmos is diamond, because you have lots of carbon atoms, and they condense at 4,400 Kelvin, a high enough temperature that you get vapor deposition of tiny diamond crystals. So you need those two things. You need to have a low enough temperature and a high enough concentration of the atoms to make them. And then at slightly lower temperature, 4,000, you make graphite. And then there are a series of about a dozen what we call the minerals. Being the ancient Mesopotamian city, which was the origin of all cities, and it's considered the origin of civilization. So this is the reference to that. And there are about a dozen minerals, all formed from extremely common elements in the cosmos, all formed at very high temperatures of condensation. And so we have these various minerals, the nitrites, the carbides, the oxides, a couple of silicates. And you'll notice that there are only 10 essential elements in these minerals. And so perhaps the most basic question of mineralogy, of mineral evolution then, becomes how do you go from a dozen minerals with 10 essential elements to what we see on Earth today, which is more than 5,000 minerals using 72 essential elements. That's the main story of mineral evolution. And we tell that story in 10 stages, beginning with the most primitive period where our nebula is forming, and you can imagine the dust and gas and the great dense molecular cloud perturbed, coming together, forming the nebula that would become our solar system. And 99% of the mass goes into the central sun, where the remaining dust and gas is orbiting, clumping together through gravity. The earliest stage of mineral evolution in this nebula was when the sun ignites, it goes into its T-Tauri phase, bursts of radiation span outward, and they basically bake and melt the tiny accumulations of dust which have come together. These chondrules, these tiny particles, then form the chondrite meteorites, in which we find about 60 different mineral phases, all very high temperature condensate phases, about half of them micro or nano scale. So we've gone from 12 minerals to the 60 chondrite minerals. And then, of course, the chondrites clump together. They form larger and larger bodies, planetesimals that might be 100 or 200 kilometers in diameter. And when you get bodies that size, they melt, they differentiate, they go through various kinds of processes of aqueous alteration. There are shock impacts as different bodies collide. And here we find the 250 minerals that we can still find in the meteorites that fall to Earth today. So that's stage 2, the achondrite meteorites. And so these then become the building blocks of planets. Stage 3 is the planetary formation. Again, large-scale differentiation, various kinds of fluid rock interactions, impacts of meteors at the surface. Now, if you have a relatively dry world, like Mercury or the Moon, it looks to us like you can get perhaps 300 different mineral species, and that's about it. That seems to be the end point for those worlds that are relatively dry. They don't have a large, volatile rock interaction going on at the surface. If you have a wet world like Mars or Earth, you can get many more phases. You can get hydrated phases, clays, hydroxides, ices, if it cools enough, evaporites, these sorts of minerals. That gets you up to about 420 minerals. And we think that may be the end point of Mars. It's hard to imagine Mars getting much beyond 400 or so species. But Earth has more internal heat. It has more interaction. And so if you have wet basalt and you partially melt it, of course you form granites. The granites then concentrate other elements, and particularly in pegmatites, this is how you get to about 1,000 different mineral species on early Earth. Mineral species that we don't think are going to occur on Mars or Moon or Mercury. Stage 5, plate tectonics, even more fluid rock interaction at huge scales. And here, because you form massive sulfide deposits, you have new modes of volcanism, you have the opportunity of bringing high-pressure metamorphic sweeps to the surface. This gets you up to about 1,500 different mineral species, all through physical and chemical processes that would occur on an Earth-like planet. But as far as we can tell, 1,500 mineral species through physical and chemical means is the end point for Earth. We can find no mechanism by which purely physical and chemical processes would get you farther than this. And yet today on Earth we have more than 5,000 mineral species. So how is that possible? The question is, how do we get to this? And the answer, it turns out, is life. We argue that life has given new physical and chemical conditions at Earth's surface that lead to more than 2/3 of all the known mineral diversity. So, this is a kind of interesting twist on an old theme. There are many different hypotheses for the origin of life, which require different kinds of minerals. And that makes a great deal of sense. But by the same token, further mineral evolution is dependent on life. And here we see the co-evolution of minerals and life through much of Earth's history. Stage 6 has to do with the very earliest period when microbes were able to accelerate chemical reactions that would occur anyway. For example, the precipitation of large iron formations. Here we're not seeing new minerals form, but we're seeing new modes of mineral formation catalyzing very large-scale sedimentary deposits, for example. The real game changer, the punctuation event in mineral evolution, is stage 7. That's the great oxidation event, where photosynthesis produces large amounts of oxygen in the atmosphere. That in turn causes new chemical reactions to occur at Earth's surface. And it turns out that most of Earth's minerals, we argue, in fact 2/3 of them, are the consequence of this dramatic change in the near surface environment. Now this claim requires a little bit of explanation and pursuit. So what I'd like to do is look at this famous diagram. What we're seeing is 4 billion years. Here's modern times going back 4 billion years. On the vertical scale is some measure of the oxygen content of the atmosphere. And what you'll notice is, a very long time ago, oxygen was extremely low. People don't normally say how low, but extremely low. Then there was a period where there was some intermediate oxygenation. That's after the great oxidation event at 2.5 billion years. And there's another oxygenation event associated with glaciation about 700 million years ago, and that brings us up to modern levels. And so one of the questions is exactly how low are we talking about? Back in the Proterozoic, back in the Archean period. But nevertheless, this new oxygenation led to conditions which leads to many, many minerals. Let me show you why that's true. There are many, many elements, mineral-forming elements that are redox sensitive, that have multiple oxidation states. First row transition elements, many, many other redox sensitive elements, and also, of course, non-metal elements. And all of those have multiple oxidation states, which can lead to a great deal of chemical diversity. Now, the key about the early period of Earth's history before photosynthesis is that you had a large amount of ferrous iron in the oceans and in soils. And when you have ferrous iron in large quantities, it acts as a redox buffer. And the buffer is, in fact, hematite-magnetite. It's that line right there. And notice where that falls on the log of oxygen fugacity. It may surprise you that it's 10 to the minus 72. So essentially no molecular oxygen whatsoever in this period. So any redox reaction that's taking place is going to be buffered by the huge amount of ferrous iron in the oceans and in soils. So if you're buffered at 10 to the minus 72, let's think about what minerals will form and what minerals will not form. So this is the kind of thing that was happening at that point when oxygenation first occurred. You had these vast deposits of iron oxides. And so we're seeing a period of a couple 100 million years where that buffer was in place, and all you were doing is just precipitating more and more and more iron oxides on the ocean floor, still maintaining 10 to the minus 72. The greatest iron ore deposits in the world are associated with this kind of buffer. Okay, so what would form? Let's look at siderite, the iron carbonate, ferrous iron carbonate. There's a phase region at STP here, and in order to form siderite, you have to be in this lower left quadrant at low enough CO2 and FO2. And basically, you have to be below about 10 to the minus 68. As that's fully consistent, we know that siderite was forming in large quantities at this period. That makes sense. But let's look at the iron carbonates, azurite and malachite. And for them to form, you have to be in the upper left quadrant here. You have to be greater than 10 to the minus 43. And that's about 30 log units away from the buffer. And so you simply cannot form azurite and malachite in Earth's Archean period. And the same kind of argument can be made for many, many different minerals. Let's just look at those copper minerals in a little more detail. You'll see the gray dotted line here is 10 to the minus 72, that's our buffer. So copper metal and many copper sulfides are stable. But when we look at all the list of copper minerals, and today there's hundreds of them, something like 600 copper minerals, there are only a few dozen that are actually stable under these conditions. The +1 copper minerals are not stable under that buffer, and certainly not any of the +2 minerals. So all of these beautiful copper minerals that you see when you go to a museum, they would not occur in the Archean period. In fact, when you go to a museum, what you're looking at, when you look at copper minerals, the beautiful ones, you're looking at the consequence of biology. And the same thing's true for almost all of the uranium minerals. 90% of the uranium minerals contain the uranyl ion, which is the result of oxygenation. Almost all the nickel minerals, almost all the cobalt minerals, and in fact, all those redox-sensitive elements, there are thousands upon thousands of minerals that simply cannot form because they require oxidation states that are much higher than that redox buffer. That's the simple argument that we make. And why would we triple the number of mineral species after the great oxidation event? One can look at it this way. This may be a little naive, but I think that it makes the point. Before the great oxidation event, you certainly were restricted, even with all kinds of fluid rock interactions and other sorts of things that took you away from the exact 10 to the minus 72 buffer. You were restricted to something below about 10 to the minus 60. Today, we have the full range. You've tripled the range of redox, and you've tripled the number of minerals. It's just simply a distribution in redox space that life has made a much greater arrangement possible. Okay, So we believe that the changes in Earth's atmosphere from about 2.2 to 2.4 billion years ago was the single greatest event in terms of diversifying mineralogy. That's stage 7. We can go on. Stage 8 is a long period of Earth's history when things seem to be fairly stable. This Mesoproterozoic, sometimes called the boring billion, saw very few new mineral species, but certainly saw a gradual change in the redox state of the oceans. And so this is the time when the oceans became more oxygenated all the way down to the depths. There was a period of glaciation, snowball Earth, that we call stage 9. Again, not a lot of new minerals, and in fact, in one sense, for the near-surface mineralogy became much simpler. It became primarily ice, which is a mineral under these circumstances. And then stage 10, the terrestrial biosphere, lots of new mineral-forming mechanisms associated with the terrestrial biosphere. Some of them have to do with biomineralization, some of them have to do with microbial activities in a near-surface environment, redox gradients, and so forth. There are some fascinating changes to Earth's mineralogy that occurred, especially on land, and particularly associated with the evolution of root systems. Root systems appeared about 400 million years ago, represented by the fossils of root systems from the Rhine chair, only about 1 centimeter long. These tiny root systems, though, penetrated down. They formed deeper soils, they formed new clay minerals, and as a result, plants could grow taller, then the roots became deeper, and the plants became taller. Eventually, you had soil horizons that, instead of being a few centimeters deep, were several meters deep. Vast root systems leading to both physical changes in the production, for example, of clay minerals, in the armoring of riverbanks, in the seeding of clouds, but also very important deep biological changes, entire ecosystems that existed deep beneath the surface, and which also then led to more mineralogical changes. Again, a feedback between the mineralogy and the biology. And just to give you a sense of the kind of thinking that is being produced by this, let's look at one possible large-scale change where biology may be changing Earth on a global scale. This is just speculation, but it's the kind of thing that I think 10 years ago could not have been published, but now is being widely talked about. So consider Earth going from this to this. And much of what you're seeing is the formation of soils rich in clay minerals. An order of magnitude increase in the amount of clay minerals in the terrestrial environment. And because of that, you have a huge amount of clay minerals that are then being eroded off the continents and into subduction zones. And some people are actually suggesting that this increase in clay minerals could perhaps lubricate plate tectonics, and that what has been assumed is a kind of acceleration of the rate of plate tectonics in the last few hundred million years may be a consequence of biology. Now, that's a pretty far out there speculation. It may not be true, but just the idea that people can think this way and propose this kind of global scale change where it is plausible that biology is affecting plate tectonics, I think that's really fun, and it expands all of our horizons when thinking about geological processes. So, the first part of my talk, these are the conclusions, that Earth is transformed repeatedly over 4.5 billion years, that the minerals that we see tell us about that transformation, and that indeed minerals have co-evolved with life over much of that period. One of the things that's fascinating about minerals, therefore, is that it's a complex, evolving system. And in this respect, it's like many other evolving systems we see at or near Earth's surface. There are many characteristics. There's seen diversification through time. We've seen congruency. We've seen periods of punctuation, but also periods of stasis. There's extinction events. And chance versus necessity always is part of the rhetoric of complex systems. Some aspects of these systems are deterministic. They occur over and over again. And yet other aspects are frozen accidents. And we can start asking, well, which are which, and how does that apply? This is analogous to many other systems. You can talk about nucleosynthesis or organic molecule evolution, life itself, but also the evolution of languages, the evolution of culture. All of these can be discussed in terms of these variables. And I now want to focus on this question of chance versus necessity in terms of the mineral evolution of Earth, and perhaps giving us some insight as to how unique Earth might be. So this brings us to this new topic, mineral ecology, studying the diversity and the distribution of minerals at or near surface. And we ask, if we replay Earth's history, how similar or different might it be? So I'm going to look at three aspects of this question of mineral ecology, the diversity and distribution of minerals. First, look at crystal chemical arguments, look at planetary stoichiometry, and finally, mineral frequency distributions, a new statistical approach to mineralogy. So let's think about crystal chemistry. And if you ask, what is the diversity and distribution of minerals, one of the key aspects is just composition, Earth's crustal composition. So plotted on the horizontal scale here is just crustal abundance of the 72 elements. Each point in this plot is one of the 72 mineral-forming chemical elements. The vertical scale is a log scale of the abundance of minerals, how many different mineral species one finds. And so there is a general trend here, just a general trend that as you increase the crustal abundance, you increase the number of mineral species. But you'll also notice there are many outliers. Most of the elements follow this trend, but there are quite a few elements that are way below the trend. And we can understand each of those elements quite simply. For example, think of gallium. The reason gallium has fewer species than you might expect from its crustal abundance is because it's masked by aluminum. And so most of the gallium on Earth's crust is a minor element in aluminum-bearing minerals rather than forming its own species. So we can understand all of the elements in this area. Some of them are rare earth elements, and there's hafnium, which mimics zirconium, of course, and so forth. They all fall below the curve for that reason. Now, there are others that have many more species than you might expect, in some cases, an order of magnitude more. And here again, we can understand it because these are elements that all have multiple oxidation states and play multiple crystal chemical roles. Think about copper. Once again, we've seen this. It can occur as a native metal, it can occur in the +1 state, it can occur +2, it can bond to sulfur, it can bond to oxygen. Copper plays many different crystal chemical roles, and as a result, has far more mineral species than you might expect just from its crustal abundance. And that's true for all of those elements that lie above. But nevertheless, there is a general trend. And we can ask the same sort of question for the moon. And here we see far fewer known minerals, only 55, but the exact same kind of trend. And furthermore, it has the exact same slope. And this raises an intriguing question. What is this implication of the identical slopes? And I want you to think now, as those of us in petrology have been taught to think, about phase space. You have pressure, temperature, and 72 chemical elements. So that's a 74-dimension phase space. And I think what we're seeing with these similar slopes is a hint that the average volume, if you will, in this 74-dimension space is more or less evenly distributed. And so whether you sample the moon with only a few chemical elements or Earth with many more, that slope is somehow fundamentally tied with the distribution of phases in phase space at near standard temperature and pressure, near crustal conditions. I suspect that if we go to higher temperature and higher pressure, there will be a different slope. Because I think there's a different distribution of phases as you get to higher dimensions. Although we haven't done many experiments with say, 8 or 10 different chemical elements at natural conditions. Nevertheless, I think there will be fewer phases, and therefore we'll see a lower slope. But this is sort of an intriguing thing. We're working with Mark Giorso and some other people who think deeply about thermochemistry to see if we could perhaps derive from first principles this slope. So that's just an aside. What's interesting about this distribution, by the way, is that it has a direct relationship to ecology. A well-known relationship in ecology is called island biogeography. And in this case, the horizontal scale, these are for biological species now. The horizontal scale is the log of the area of islands that are closely related to each other. For example, islands in the Caribbean. And the vertical scale, again, is the log of the number of species. So this is exactly analogous to what you've just seen for minerals. But what we're suggesting is that perhaps the area of islands in its relationship to biological ecosystems is somehow analogous to the compositional volume in that 72-dimension space for mineral species. And so there seems to be a very similar relationship. Something that's fundamental about the distribution of species in relationship to how much volume or space to expand in, you might say. So this is an intriguing relationship that we're going to explore further. Okay, so that just shows you that there is some logic to the distribution and diversity of minerals. I now want to consider planetary stoichiometry, because what we've just seen is that the near surface, the crustal composition, plays a huge role in what minerals you see. Recent discoveries in astronomy have shown that there are very different compositions of what we call Earth-like planets. And if composition is so important, think about this. So if you look at the ratio of elements in stars, in sun-like stars, what you find through spectroscopy is there are some very dramatic ranges. For example, the Mg over Si ratio of stars can vary from things very close to our sun, which is about 1.2, to less than 0.5 or greater than 2. Now, as petrologists, we all know the implications of this. If you have an Mg over Si less than 0.5, you're going to have a lot of silica, a lot of quartz or some high-pressure formula. If you have an Mg over Si greater than 2, you're going to have a planet that's dominated by olivine. And so, consequently, the mantle mineralogy is very variable and the dynamics will vary. So let's just, for a point of reference, consider a planetary system that, rather than Earth's 1.2, has an Mg over Si of 2, something that's very plausible that we see in the cosmos. And the consequence is well known to all of us. As you melt an olivine, the first melt is iron-rich, and therefore it's denser than the mantle from which it's derived. And then rather than a basalt magma that rises to the surface and forms a crust, the first melt of this planet will sink. So how do you form a crust? The questions abound when you have this. If you have this, what's the mechanism of crust formation? Is all the water going to be sequestered in a wodzillite or a ringwoodite phase that's dense and therefore is sequestered in the mantle? Can you even start subduction in such a world? And what about redox gradients that might form? And so then if all of these things are essential to life, and some people suggest that plate tectonics and redox gradients and dynamics of this sort are essential, then could life even form on a planet that has an Mg over Si of 2? And yet every astronomer would argue that an Mg over Si 2 world that had the same size and density of Earth was exactly Earth-like. That's the astronomical definition. But it isn't really Earth-like, is it? At least not from our perspective. Well, let's look at other elements. Just pick out one of them, calcium or magnesium. Chondrites, about 0.1. Earth's crust, 1.7. The moon, about 0.2. These are radically different numbers. How does that affect the mineralogy of the mantle of the crust if you have these kinds of variations from one world to the next? Again, all considered to be Earth-like from an astronomical point of view. And yet we know as petrologists, they're very, very different worlds. Okay, so this raises this question of Earth-like. What does it mean? I leave that question open and for you to ponder, but let's look at this third aspect. And this has to do with mineral frequency distributions. And this is the heart of our mineral ecology work. It turns out because we have huge databases on minerals, we can start asking questions about diversity and distribution from a statistical point of view. So based on the first experiments we did, this was about a year ago, we had 4,937 mineral species. We had 150,000 localities, and very importantly, we had over 650,000 mineral locality pairs. That is, calcium carbonate from a particular quarry in the Paris region. So if you have 650,000 data, you can start doing statistical studies of distributions of minerals. And we're looking for quantitative relationships between mineral diversity and distribution. And what we find and it's quite surprising, is the distribution of those 5,000 mineral species across Earth's surface is, in a mathematical sense, very similar to the distribution of words in a book or biomass in an ecosystem. Let me show you what I mean. Consider a redwood forest. And when you look at this forest, you realize almost all the biomass is in redwood trees. Just as in terms of mineral distribution in the crust, almost all of the mineral mass is in feldspars, silica, kerosene, amphiboles, of just a few common minerals. 99% of Earth's crust is just a few dozen minerals. And yet, the diversity is in small, rare things. So if you want to describe a redwood ecosystem, you really have to focus on those tiny things. You could also think about it in terms of words in the book, and it turns out mathematically this is the most direct analogy. This is the statistics that we use. So most words are common, a, and the, but it's the rare words that define the diversity and the authorship. And fortunately for us, because the National Security Agency of the United States is extremely concerned about analyzing emails, these statistics for word distributions have now been raised to a very sophisticated level, and many of these statistical methods are now available to us, and we can apply them directly to mineral distributions to predict what's missing. Let me show you what I mean. Okay, first of all, in terms of the distribution, what we have here on the vertical scale are dots representing minerals from an exact number of localities. Minerals from exactly 2,000 localities. Minerals from exactly 5 or 1 locality. But what you see is there are few minerals that are known from many, many localities in these databases. Others known from thousands, others known from hundreds. But most minerals are known from very few localities. 8% of all known mineral species are known from exactly 3 localities. 22% of all known mineral species are known from exactly 1 locality. And this is a classic large number of rare event distributions. So, another way of putting this is the cumulative probabilities of having one locality, 1 plus 2, 1 plus 2 plus 3, and so forth. More than half of all mineral species are known from 5 or fewer localities on Earth's surface. These are rare minerals. So, a few common minerals dominate the crustal volume, but most mineral species are rare, and these rare minerals follow a statistical distribution known as a large number of rare event frequency distribution. We've managed to model this, and the consequence is you can make all sorts of statistical predictions because of the beauty of these functions. Here's what the function looks like. Here we see this distribution. Here are the number of mineral species known from exactly 1, exactly 2, exactly 3, up to 15 localities. In black, you'll see the actual numbers, the statistics that are found in a database called vindat.org, which lists those 650,000 localities. In red is our model, proposed by Hazen et al. And this allows us to do what are called accumulation curves, which are well known in biology. Here's one that's done for biological species. Imagine going to that redwood forest and you look at those small plants at the base of the trees. And you look at species of the first and the second and the third, you count 1,000 individuals, 2,000 individuals. And each time you count one, you see if it's a new species. Early on, you're adding species very quickly, but then it tails off. And you can use these statistical methods to find out the total species diversity, even if you haven't looked at every plant in the forest. You can do the same thing with genomes for microbes. We measure many microbial genome sequences. You can predict the total diversity of microbes, even though you're not measuring every single microbe. You can do the same thing for minerals. And so what we have here is, this is the number of mineral counts. We're at about 650,000 mineral locality data right now. So right at this point. On the vertical scale is the number of species that are known. Early on, you add species very quickly, but the more and more locality species data you have, the fewer new species are found. This starts tailing off. As of February 2015, we were at about 5,000 mineral species with 650,000 counts, but we can extrapolate into the future. And what it means is we now know that there are about 1,500 missing minerals on Earth. They exist on Earth today but have not yet been found by the techniques which are now being employed. This is a minimum number because, of course, new techniques will be brought to bear. And furthermore, ironically, because we're predicting what minerals are missing, people are going to go out and specifically look for them. That's a new set of protocols, which means we're going to find minerals at a faster rate than would have been done in the past. But nevertheless, this allows us to ask a lot of questions. For example, what are the missing minerals? And so we can do the same statistical methods on subsets of all minerals. Here, for example, are the 400 or so carbon-bearing minerals. And those mineral species give you a nice statistical distribution. It allows us to extrapolate that as of today, with 403 carbon minerals, 83,000 counts or so, we now can extrapolate there are about 145 missing carbon-bearing minerals. And in fact, the Deep Carbon Observatory has just initiated a global carbon mineral challenge. We've written a paper which is now in American Mineralogist, which describes the 145 missing minerals. We predict what many of them are. We have tables of missing minerals. We can tell you where to go to find them and what you might find when you get there. So for the first time in history, mineralogy we've been making specific predictions, and I just found out that at least 3 of the minerals we've predicted to find have now been found in just 3 months. So,
how do you do the where?
Excuse me?
You
do the where by looking at the statistical distribution across the globe, finding that there are certain localities that have an extreme abundance of, for example, rare earth sodium carbonates. Well, our statistics show that there should be at least 5 rare earth sodium carbonates that have not yet been found. What you do is you go back to the museum drawers. You don't even have to go to the locality. You go to the museum drawers that contain those specimens, and you look in detail for white, poorly crystallized things that you just would have overlooked before. And we predict they're going to be there. In fact, this is what's happening. So the museum collections become the prime source of new carbon minerals, at least to begin with. And we can, for example, predict go to Lake Natron or Algonia Langai to find certain rare carbonated minerals and so forth. Go to the Poudret Quarry in Quebec, where there are 82 known carbon-bearing minerals, and all of the known strontium carbonates are there, but we predict there should be a couple more that haven't been found. And they're known synthetically, it's just they haven't been identified, so we can tell you what they are. So clearly there'll be surprises, but this is an opportunity for us to be much more proactive in finding and identifying these new mineral species. So if you're interested, I can give you a copy of that carbon mineral ecology paper, which describes in great detail how this works. Okay, so now let's talk about probabilities, because that's really this idea of chance versus necessity. Is Earth's mineralogy a deterministic thing, or is it a frozen accident? And what we'll see is that, in fact, that's a false dichotomy, that the question is much more subtle and it has to do with probabilities. So we can predict the probability. It turns out there are about 2,800 minerals that are extremely likely, greater than 90% chance to occur if you replay the tape of Earth. And so here we see, this is all 6,400 minerals that are predicted to exist on Earth today. There's another group that are likely, greater than 50%, but still not 100%. And there's another group that are fairly low probability, or less than 50%. And if you think about this in another way, look at this curve. There's deterministic, that's necessity, probability almost 100%. There's others where frozen accidents, less than 10% probability to find those minerals. But there's this huge range, which is neither chance nor necessity, it's just probabilities. And that's what you expect, really, for any distribution. Each of these minerals represents a chemical reaction, some of which are extremely likely given the chemistry and the environmental conditions of Earth. You're going to form albite, you're going to form muscovite, you're going to form quartz in any Earth-like planet. There are others that are extremely improbable because they involve juxtapositions of extremely rare elements in unique chemical environments, and others that just sort of are kind of in the middle. So this idea then is that chance versus necessity is a false dichotomy. So every one of these minerals represents chemical reactions. Some reactions are more likely than others. So what if you replayed the tape, or is there another Earth-like planet? So these are questions we've been asking. First of all, I want you to remember that there is no other planet that's going to have the exact same chemical stoichiometry as Earth. So if you have different bulk and crustal compositions, you're going to have different tectonic histories, certainly different evolution of the biosphere. And another factor, which is sort of an amazing thing, we may have 6,500 species on Earth today, But there are many thousand, perhaps 10 or 15,000 additional mineral species which are highly plausible if you look at many different Earth-like planets, but just don't happen to exist on Earth today. So we estimate about 20,000 different plausible minerals that would occur in the cosmos. Some of those minerals are going to occur on other planets, not Earth, and some may have existed on Earth in the past that have eroded away. Some may exist on Earth in the future, but have not yet formed from chemical processes. So you have to think about this through time. So there's a lot of combinatorial variation that's plausible here. So our analysis so far only includes these 6,437 minerals. It doesn't include any of those 10 or 15,000 plausible minerals that may occur. And so this really starts raising the combinatorial estimates. But let's just focus on these 6,437. Oh, by the way, this is just the analysis. When you think that every chemical element could form at least 1,000 inorganic compounds, we know this is true just from the inorganic tables of crystalline compounds. And in beryllium, there are 100 known beryllium minerals, but even though beryllium sulfate is something you can buy from any chemical reagent store, no one has yet found beryllium sulfate on Earth. There are no beryllium minerals with copper or nickel or molybdenum. That's really surprising to me. We know that you can form compounds of that sort. So it's just a matter of finding the right chemical niche where you have a pegmatite that's been intruded by a sulfide, copper sulfide-rich fluid or something like that, and then those minerals will form. So there's lots that can be produced. If you have an average of 4.7 chemical elements per mineral formula, you just basically multiply 72 times 1,000 divided by 4.7, and that gives us these 15,000 plausible species. That's just an aside. Okay, so more than 10,000 plausible minerals, only a fraction of those species occur on Earth. Some are going to be extremely likely. Some are going to be extremely unlikely. There's a statistical distribution that's going to follow that LNRE distribution. And so you can do a calculation. You can multiply the probabilities out and say, okay, if you rediscovered, if you came to an Earth-like planet, you rediscovered the first 5,000 minerals. What is the probability to be the same as what we find on Earth today? And I don't think it should be a surprise to you that it's extremely unlikely, the combinatorics for such. When you do the calculation, it's less than 1 in 10 to the 300th power that you come up with the same mineralogy in detail. Sure, the top 500 minerals will be the same, but the rare things, the things that really make Earth stand out as unique, are different. And I think that's a realization which is kind of fun. So I've got a couple of conclusions here. The diversity distribution of minerals is a consequence of both deterministic and stochastic properties. There's physical, chemical, biological processes, and so this idea of chance versus necessity really is a false dichotomy. If you played the tape of Earth again and discovered 5,000 minerals anew, the statistics show that at least 25% of the mineral species would be different from the ones we find today. And that's assuming an identical Earth-like planet, not some other astronomically, quote, Earth-like, unquote, planet, which we know clearly is not going to be exactly like Earth. And finally, and this to me is the most fun, that if you think about Earth, we know it's unique in its biosphere. And we value Earth for that reason. But Earth is equally unique in its mineralogical kingdom as well. We live in a very special place. So thank you very much, and I welcome questions.